up today by National Park. And of course, the Tourist Council wants to promote it to say that not all the island's black, and in fact, only a little bit's been burnt. So I'm going up there to do a quick evaluation, but I can't go because I've got some other things to do until Thursday, so that might be too late. But yeah, hopefully this might prompt both the local landowners and national parks to support a bit more research there.
Yeah, it'd be nice. Still got your
Yeah, we've submitted a number of proposals there to get approval. So hopefully the fire will provide the impetus that we need to continue with it.
What do you want to be able to do there then?
Oh, we've got a whole series of plots that were put in years and like 60 or 70 years ago, like we've got in the North Queensland rainforest. And so we want to keep monitoring those and then do some more work on disturbance and continue with the fire work, but basically and looking at changes due to the impact of disturbance from fire, logging, cyclones, whatever, climate change, which is the new big thing. So we've, there's not many places around where we've got really long-term data sets going back 65 years, I think.
Hardly any.
In 3 forest types, so that's quite useful. Yeah. And now I've just finished publishing my book on the vegetation of Fraser Island. We're hoping to use that to try and work with the landowners there or the bachelor people to look at what traditional uses were of some of those different species and parts of those at different times of the year. The Aboriginal groups used to come there primarily in the winter months, or the tourists would come in like they do now in the winter months when it was lots of fish and lots of crabs and et cetera, et cetera. So yeah, we'll see how that all pans out.
Yeah, I hope it comes well.
Yeah,
I would say we get free advertising every year when something burns. So
yeah.
Sorry, Bu Ati.
Time to start.
Now we are already 8. Maybe we could start. Thank you.
3 menit lagi mungkin ya Pak ya, kita tunggu sebentar. 8:05 sebentar.
Pagi Bu Ati.
Pagi. Attention please, the meeting is going to start in a few minutes. Please turn off your microphone during the meeting. Thank you. Kita mulai saja ya Pak ya.
Ya, silakan.
Bismillahirrahmanirrahim. The Honorable Indonesia National Coordinator, Professor Bambang Hero Saharjo, the Honorable Principal Investigator, Professor Marco Kren, the Honorable Secretary of Department of Silviculture, Dr. Erianto Indra Putra, our Honorable speakers, Professor Robert Jackelson, Associate Professor Graham Applegate, Professor Bambang Hero Saharjo, and Dr. Israel Albar. Also distinguished participants. Assalamualaikum warahmatullahi wabarakatuh. Good morning for Indonesian and Australian participants. Good evening for participants who join us from United States. Welcome to the third international webinar, Peat, Fire, and Smoke. My name is Ati Dwi Nur Hayati. It is wonderful and precious chance for me to be your master of ceremony in this morning on Tuesday, 15th of December 2020. This event is held in collaboration between UMCES, NASA Tropical Peat Fire Research, and Department of Silviculture, Faculty of Forestry and Environment, IPB University. First of all, I would like to thank everyone here for attending to the third international webinar. On this morning, several agendas. The first agenda, opening, and fourth agenda is closing. Excellencies, ladies and gentlemen, step on to the following agenda is welcoming remarks. The first is welcoming remarks from Professor Bambang Hero Saharjo as Indonesia National Coordinator. To Prof. Bambang, please, time is.
Okay, thank you, Bu Ati. Ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Good morning. First of all, we welcome Bob Jackelson here. He is my old friends. And also the other speakers. We have Graham also. And also we are lucky today. We have Pak Israr, who will talk about how Indonesian government link with the forest fire preventions. And also Marco Kren as team leader for the UMCES IPB Tropical Peat Fire Project. Today is the third webinar, the international webinar. I think this is the last webinar. And today also we will talk about one of the sexy issues that is regarding the issue on smokes, especially from peat fires and linked with the haste and also the calculation on it. Again, we thank for all your participants, and hopefully what we have done for all the participants, since we have the first and the second and third webinars, is make you satisfied, hopefully, like that. And then we do hope that this is our ways to share our result of research. Is not only depend on paper or the journal paper directly. Maybe part of you just read the names of famous Bob Jackelson, but now you can communicate directly to him. And then as Indonesian coordinators, we thank for all your participants and please enjoy the webinar. Thank you very much. Terima kasih.
Okay, thank you, Prof. Bambang. So the second welcoming remarks will be delivered by Principal Investigator. To Professor Marco Kren, please, time is yours.
Well, again, I just want to thank everybody for participating here and coming on board and seeing what we're doing. All of us get to get a better view of what all the different people in the project are doing too. Since we do our parts, but often we don't know what everybody else has been doing. So even for all the members of the project, it's been a real good opportunity to get acquainted and start seeing where their results are showing up. But it's also a great opportunity here for us to interact with people outside of the project and inform them of what's been happening with us and what we're hoping to be able to do as we move forward. And we're doing pretty well for a third go around on the webinar here. And I just sent in a report today for NASA telling them that this is one of our activities. So I think Pak Bambang said it well here about what we're doing and how we welcome everybody. And I just want to basically say the same thing and say that we're happy to have you here, and I hope you're going to participate and enjoy what we're covering. So with that, I'll end. Thank you.
Okay, thank you, Prof. Mark. Excellencies, ladies and gentlemen, before we start the next agenda, we would like to invite all participants to join the photo session. So kindly please turn on the video for a moment. Robbie, please take a picture.
Thank you. Okay, on video. 2 slide. Okay, 1, 2, 3, cheers. 1, 2, 3, cheers. Okay, 2 slide. Okay, 1, 2, cheers. 1, 2, cheers. Okay, thank you, Bu.
Okay, thank you, Robbie. Well, ladies and gentlemen, now we will start the second agenda on the third International Webinar 2020. For the presentation session, will be hand over to our moderator, Dr. Erianto Indra Putra. Pak Indra is Secretary of Department of Silviculture, Faculty of Forestry and Environment, IPB University. To Pak Indra, please, time is yours.
Okay, thank you so much, Bu Ati. Assalamualaikum warahmatullahi wabarakatuh. Good morning and for the Indonesian, good evening for the US participant, to Bob and Mark. So we are happy here to see you all again in this webinar series. So we are very happy today that we will have 4 speakers for today's webinar. We will have Professor Robert Jokelson. We know him as Bob Jokelson. I think we are very happy that Bob can join us today, as Bob I think is very busy for nowadays. And also we have Graham Applegate from my Australian uncle. Yeah, good morning, Graham. And we also have Pak Bambang here and also Pak Isar. So Pak Isar, thank you for attending us, and we are very happy. We are very glad that the DG allowing you to join your expertise today. Okay, for the first speaker will be from Prof. Robert Jokelson. Prof. Robert Jokelson is the research professor from the Montana University at Missoula, Montana, USA. So he will briefly present his finding and result from his analysis of the smokes from peat fires in Indonesia. Okay, Bob, time is yours.
Trying to share my screen. Is that working?
Yep, I think so.
Okay.
Yes.
So turn on. Okay, has everyone seen my screen now?
No, not yet.
No, Bob.
Okay, Scott, I'm looking at the slides. Let me,
Yeah, there's a share screen button that's green down the bottom of the page.
right, I hit that.
It's not coming up.
Oh, okay, maybe I have to select the screen.
Yeah, after you do that, you go to the screen that you want.
Yeah.
Okay. So are you seeing anything now? Select a window or an application. I usually don't have trouble with this. Let me, whoops. Screen. I've selected screen a bunch of times. Well, let me see if I choose. Oh, maybe I just have to say share too. Okay. Did that work?
It started
Yeah,
to.
looks like it's getting there.
Oh.
There we go. We're getting there.
Okay, sorry about that. The
Just need to go on presentation. There it is now, Bob.
There you go.
It's
okay,
good.
so
It's
okay,
good.
great. Sorry,
Okay, everything is
sorry
good.
it took so long. I'll go quicker.
Okay. It's
So
fine, Bob.
first, I want to thank everybody for organizing this and for getting all the great data that I'm able to show, and start off the talk by going through the instruments that we use quickly. So across the top is gases and across the bottom is the particles from the Indonesian peat smoke. And these here you see are whole air canisters, we call them, and they're evacuated, and they're the most portable way to measure important gases like CO2, methane, and many other important gases. And you open them in the field in the smoke plume, and then they're returned to the University of California for analysis. But there are some important gases that we can't measure with these WAS canisters. And for that, we brought to Indonesia this rolling FTIR system, which can measure things like ammonia and formaldehyde that are very important. And so between the two of these, we can measure virtually all the gases except the ones that you would need a mass spectrometer for. And I'll talk a little bit more about the mass spectrometry later. Below that, we have, these are the filter holders where we can put filters in here and collect the solid and liquid smoke droplets out of the air. And this is the best way to measure the mass per volume of smoke, and also to later analyze what's on the filter for the chemistry of the smoke particles. And so that's very useful, but it's not a good way to measure how the smoke particles interact with the solar radiation and impact the climate. And so for that, we also brought to Indonesia in 2015 these two laser-based systems that allow us to measure how the smoke particles absorb or reflect visible or UV light in real time. So that's the extent of the type of work we can do in the field. And here's some pictures of the sampling from 2015. And so you can see we're getting a lot of the smoldering peat, and a lot of people in this webinar were helping with this. And we were definitely not concentrating on the flaming, the stuff that makes it into the news a lot of time. We were trying to get the peat itself, because there's already a lot of data for the other vegetation. And the peat is also often anyway, the dominant part of what's burning. But we want to be able to use even more than what we did in the field. And so we also collected samples of peat in the field, or the team did, and then shipped them to Missoula. And here we can see down here, two kinds of peat samples that we typically get from Indonesia. These powdery ones are actually kind of hard to burn. And then these ones that are like bricks or brownies, we call them, they're a little easier to burn. And that's something we've figured out over the years. And then when we apply a propane torch for about 5 or 10 minutes to one of these brownies or peat samples, it will eventually begin to sustain combustion on its own. And then here's that happening underneath a hood in the fire lab that I'll show more pictures of in a minute. And so this is making peat fire smoke that's, it's got that white smoldering smoke that's similar to what you see in the field. And so here's an introduction quickly to the Missoula Fire Lab. On the right, you can see the fuel bed. This is what we call the stack. We pressurize this room with air and then we open a hole in the top of the stack so the air flows up the stack and it brings the smoke past the instruments that are like about over 1,800 kilograms on the platform. But if we want even more people, we can put them in the rooms next to the fire lab and even have some parked outside that sample smoke in the lab through a hole in the wall. So this gives us potential to basically bring virtually any analytical technique to bear on smoke samples. And we always try to include peat as one of the fuels that we investigate in these experiments. Here's one more picture. This shows this is instruments installed on the sampling platform in the wind tunnel room, the control room, the viewing room, and even here's a truck converted into a lab that's sampling smoke in the lab through a hole in the wall. So this is just an idea of how much additional stuff we can do at no cost to the project to learn more about the peat smoke. And a few more slides to illustrate that. These slides, each row is an advanced instrument and typically represents a graduate student spending 4 or 5 years getting their PhD operating this. And so I'm not going to go into detail in all of them, but I just do want to show off how much additional type of work we got done on the peat smoke, because I think that was a nice feature of this project. We had a really good team in the field measuring peat, but we also leveraged that to, the peat samples to get additional information from unique attributes that we have in the US. So now a little history. This is going to go back and, what are some of the major results that we've gotten over the years analyzing the peat smoke. The picture on the right here is from 2001, and this is inside the stack at the top of the sampling platform. And in between this mirror here and this mirror here, we shine infrared energy that bounces back and forth and measures what's in between the mirrors. And we use this setup to make the first ever emissions measurements for gases and particulate matter from tropical peat fires. And this was the sample of peat that Dr. Saharjo sent us from Teluk Polai and Sumsel. And we actually tried burning it. It's kind of powdery and we weren't very good at igniting peat yet. So we burned it on the fuel bed and we couldn't see anything. So we brought it up here and put it right in between the mirrors and got some nice data that's still used by IPCC and a lot of fire inventories. But then we had a real progress in 2015, and I'm not sure why my slide is not advancing here. Maybe next will work. Okay, right, in 2015, we finally, after trying since 1994, hoping to do peat fire sampling in Indonesia, Mark and Indra and Bambang and the team actually made it happen. And we got the first detailed field measurements ever of tropical peat fires. And so we were able to get the emission factors for gases, particulate matter, and climate relevant optical properties of the smoke, as I mentioned in the earlier slide. And some of the results were that the emission factor for CO2 and methane were revised downward by 8 and 55%. The emission factor for black carbon, which some people may call soot, it's the black smoke you see, was revised downward by 86%, thanks to the laser-based technique that we brought to Indonesia. And we also made the first measurements of how the smoke interacts with UV light, and the first measurements in the field of important hazardous air pollutants like benzene and formaldehyde. And while we were at it, the team measured how deep the peat was burning, which is important for scaling up these measurements to a regional result. And so a little bit closer look at some of this data. On the right here, these are some of the climate forcing agents, and they're ranked by their importance. CO2 is the most important one, black carbon is second, methane is third, and clouds also impact the climate. And here you can see between the 2001 lab experiment and the 2015 lab experiment, this is when they were published these years, that everything went down, which is good. It doesn't mean we're not concerned about these emissions, but it means they're not as large as we originally thought. And we also got results that I'll explain later, showing how the clouds impact the climate and how the clouds are impacted by the peat smoke. On the left here, though, we do see that there are a lot of toxic gases in the smoke. So hydrogen cyanide, benzene, formaldehyde, acetaldehyde, none of those are good for you. The one that we found was probably the most concern was formaldehyde. The other thing we did once we had field data was we were able to compare the field results to burning Kalimantan peat in the lab and burning Sumatran peat from South Sumatra in the lab. And I just want to show a brief example of how that went. If we use methanol here, which is this one, you can see the green is the field results, and there was a lot of sampling, so we got a pretty big range. And the lab study had less samples, but they fit into the range from the field pretty well. But the Sumatra peat sample was outside the range of that. And so this leaves us with an interesting question at this point, and that is this Sumatra sample an outlier, or is it close to the real average if we'd had more samples for Sumatra? And so that's led to the next big question that we'll get to later in the talk, and that is we need more sampling regionally and temporally around the Indonesian archipelago to answer this question and see what really is the best average value and how much difference is there. So the other part of the 2015 field measurements was the smoke that we sampled onto the filters. And here you see an example of a clean filter, and then after 75 liters of smoky air. And this is not peat smoke. Peat smoke is yellow, but it's harder to see. So this is normal, typical blacker smoke. But that's just an example of how we collect the smoke, and then we can weigh it, which gives you the most accurate field measurement of how much particle mass is emitted by these fires. And then we can cut open chunks of these filters and analyze them chemically, and we get something called tracer ratios. And I won't go into a lot of detail on what tracers are, but those are marker compounds that are unique to the peat fire smoke in certain combinations. And they allow us to then look downwind, someplace like Palangkaraya, Jakarta, Singapore, whatever, and you can analyze the smoke, the pollution there, and you can figure out if 20%, 50%, whatever percent came from peat fires somewhere. And so this kind of data, the tracers are important. Other things that we measured in the particles are PAHs, which are important for health impacts. We also measured how soluble the particles are in water and found that they're low solubility, which I'll talk more about how that means they tend to suppress rainfall. And so these are some of the highlights from the particle studies. And then here's more about the optical properties, I'm sorry. This is a result from the, I'm losing my, here, I think I got a laser pointer here, right? Laser pointer. So here the peat, this is from the 2012 lab study, burning Kalimantan peat. And the peat, there was a whole bunch of different fuels that we burned. The peat is the black diamonds. And you can see they're all up here on this graph on the left. And what this is telling you, this SSA at 660, this is the fraction of visible light that is reflected and tends to cool the climate as opposed to being absorbed. So you see peat is the most cooling and the most reflective, highest albedo smoke of the whole study. And that's in the visible wavelength region where most of the solar radiation is. If we go to the UV, this graph is pretty complicated to explain, but basically a high value of the AAE, or the angstrom absorption exponent, means that you have more absorption of UV light. So just as peat is the least absorbing of the visible light, it's the most absorbing of the UV light. And the field data is in black for peat, black diamonds. And some of our field points this is our extreme point and this is our average. So we have pretty good agreement that peat does absorb in the UV, which cancels part of the cooling effect of reflecting the visible, but there's less UV than visible light in the solar spectrum. Another thing we did was take some of the filter samples we collected in the lab, and the team from Berkeley that was working with us brought them to the advanced light source. And so this is a whole building where you accelerate electrons to develop a super powerful light beam of any wavelength you want. And that allows you to do unique analyses of the compounds that are absorbed onto the filter. And in fact, they were able to analyze 392 compounds in the peat smoke. And those results are pretty interesting. There's this is all the data from all the fuel types. And the peat is shown here, was fire number 55. The first thing you notice is the red bar is really big. And that means it's high in long chain hydrocarbon compounds. They're called aliphatics that are water insoluble. So that agrees with the fact that the particles didn't dissolve well in water. Another thing is that the sugars are the light green here. And notice peat has the lowest sugars. And sugars are soluble, and they're also what's in fresh biomass. And of course, peat is the oldest biomass. So over the millennia that this peat was being deposited and building up, the sugar has been basically removed compared to all the other smoke particles. This dark green bar is also one of the bigger ones, and that's consistent with the UV absorption because it's usually nitrogen compounds that absorb in the UV. A few more things from the lab. One thing we did was do the first ever high resolution mass spectrometry of the gases from peat smoke. And in an earlier experiment, we had been able to identify 37% of the organic gases by mass, but by switching from unit mass resolution to high mass resolution, we got up to 63%. And then we did even better combining what we call two-dimensional gas chromatography with mass spectrometry. And this study actually broke the record for the most compounds ever analyzed in a smoke study. And I'll show you what that looks like here. This is a two-dimensional chromatogram. And so what you do, you inject the smoke in one end of a column, and the compounds come out based on how long they're retained in the column, based on their molecular properties. And most GC, gas chromatography, is one-dimensional. So it would separate these peaks based only on the volatility, which is this first dimension here. But you can see that there would be a lot of overlap with these other things that have the same volatility, but different polarity. So this is an approach where you can separate by two molecular properties simultaneously. And this enables us to get differences between compounds that have the exact same mass, but are difficult to differentiate otherwise in the smoke. So a quick example, alpha pinene, that's what you smell when you smell pine trees. Limonene is a different chemical, that's what you smell when you peel an orange. They have very different properties in the atmosphere, and this is basically the best way to try to find out how much of those two different compounds there is in the smoke, because they have the exact same mass, and so mass spec, FTIR, or other ways can't do that job. So now just going back to a list of some of the extra work that was done using the lab data. You can see there's a lot of them. If anyone gets interested, like how did the Malaysian peat fires compare, or what were the details of this, these are mostly in open access journals, and I can tell people how to locate any of these papers. I'm just going to talk a little bit about one more of them, and that's this one here, because this is the only measurement of the size distribution of the particles. How big are the particles? And that's important because that really affects the effects on rainfall and climate. And so I'll show a picture of that here. The background here is that clean clouds that have potential to form a lot of rain typically have about 200 large cloud droplets per cubic centimeter. On the other hand, smoky clouds typically have about 1,000 much smaller droplets per cc. And those smaller droplets make the clouds more reflective, which cools the climate. It also means that the droplets are less likely to grow to raindrop size, and so it suppresses rainfall. And this brings up an interesting problem that if you have a drought causing more fires, and then the fires make more smoke, and then the smoke makes the drought worse. And this is something that we actually see happening. And the picture here is just for fun. This is not peat smoke. The ships, when they go across the Pacific Ocean, make pollution in narrow trails, and the pollution causes the same cloud brightening effect that the peat smoke does. It's just easier to see from outer space in this image. So one more, this just shows there's a lot of important papers that we're going to go through and summarize when we do our final reports on the peat smoke. And now on to the new data. In 2019, spurred by the need to learn more about the spatial and temporal potential for variation in the peat fire emissions, a number of the team were involved in filling almost 100 sample canisters throughout various locations in Indonesia, listed here. And the other thing, before I show some of that data, which we just got, is there's still about almost 30 more canisters still in Indonesia, and we can be thinking about what we want to do with those. Do we want to go back to some of these sites, try to get coastal peat, or I'm thinking it might be, if we could, try to get some early dry season data. But first, let's look at the data, this wonderful new data we have already. And here's a typical example. These are the 22 samples from South Sumatra. And what I've done here is I've plotted the CO2 concentration, the CO concentration versus the CO2 concentration. And I do that because the slope of that plot gives you an estimate of the CO to CO2 emission ratio, which is important information about how the combustion is working, along with the modified combustion efficiency parameter, which is we can calculate directly from the CO to CO2 ratio. And this data looks really good. It's highly correlated. It fits along the line well. And that's what we always see when we have a well-sampled combustion source of any kind. So that's good news there all in itself. And now we can take these kind of plots for the different sites and start to learn about possible differences between the sites. And I've tried to put that into a table here. And so I don't know how easy it is to follow along, but I'm going to try to walk through this table because I think this is pretty interesting. And also first, though, this is very preliminary. The N, which is the number of samples, is the number of plumes for some study and the number of canisters for others. And the variability is just quoted from the literature or from the standard error of the plots right now. So it's preliminary. I haven't made everything treated exactly the same yet, but it's still meaningful. So if we go to the first two rows, we can see that the methane to CO ratio between 2019 and 2015 in Caltech were pretty similar. The combustion efficiency was a bit higher in 2015, but there was a pretty big variation. And so 2019 falls within the variability observed in 2015. But now we start to see some differences when we go to the lab fires that we burned in 2012 and 2016. In both cases, the methane to CO ratio was higher and the combustion efficiency was higher than what we got in the field. And so this could be partly because the peat dries out while we're storing it before we burn it, or there's other things that could contribute to that. It doesn't mean that the lab data is useless. It just means we have to be careful how we use it. Now we come to South Sumatra. Finally, we have more than one sample from South Sumatra. We have 22 more. And when we average them all together, we find out, oh, it's not too different from Caltech after all. The MCE and the slope are pretty similar. So that's kind of cool. That's kind of a neat result. But then again, when we look at this comparison to what we burned in the lab, very small sample in the lab, but again, the lab values were higher. And then I found a study where they burned Malaysian peat where they sampled Malaysian peat fires on the peninsula, but also shipped peat from Malaysian Borneo to a different lab, not our lab. But once again, the lab results are higher in MCE, but not too different for here. And then the last two ones I looked at, this got even more interesting because Jambi and Riau had actually seemingly lower methane to CO ratios and lower MCE values than the Calteng and Sumcell. And so this may not be statistically significant for Jambi, but I think there's a bigger chance for Riau that it is, because this is a small variability. If you add this value to here, it's still a lot smaller than any of these other values up here. So this is ongoing work just starting that will be augmented by more results. And one possible reason why we might want to think about early dry season is these are the Riau and Jambi results that had lower MCE and lower methane emissions. And they were sampled by the team in September and early October of 2019. Whereas the ones that were a little bit higher were mid-October to mid-November. And this was mid-November up to mid-November also in 2015. So that's kind of a glance at, just got the data a few days ago, started looking at it. It looks pretty interesting and I'm looking forward to looking at it more. And so with that, I want to thank everybody again that helped to get this great data and put on the webinar and take any questions. And I think I should stop sharing for the questions. So I'll do that.
Okay, thank you so much, Bob. It's a very interesting talk and so much result and findings that you share with us today. I see there is some question already appears in the chat room, but please hold on your questions because we are going to hear for the another speakers, Pak Graham, and after that Pak Bambang, and the final one will be Pak Isar, and after that we will have quite enormous time for the quick and answer discussions. Okay, Pak Graham, time is yours now.
Okay, thank you very much, Indra. I'll just try and share this screen and we should be underway. You see that okay?
Okay.
Yeah.
Hello?
Sorry, I went over.
Good morning, everybody. In light with the third series of webinars, which is really the field-based sampling. We heard in the first two a lot of the satellite imagery, remote sensing work that the team's been doing. Bob talked about the sampling for gases and particulates. And now I want to talk more about what we've done in terms of monitoring the fires themselves and gaining a better understanding of what's causing them from both a biophysical and a social point of view. So this is what I'll talk about this morning, and I'll proceed. So we all know that for each year, thousands of hectares of peatlands are burned and drained, and as a result, we get very large emissions of greenhouse gases, and as we saw, a huge number of other gases and particulates that come from these peat fires and also from some of the surface fires on the peatlands. And this causes this enormous amount of problems for our health of the local communities and disrupts the economy and affects generally millions of people in Indonesia and its neighbouring countries. And we saw from some of Bob's work how things such as formaldehyde and a couple of other gases are really noxious and very, very dangerous to human health. So as you heard of I think Indra's introduced the project and Bambang and Mark, and but one of the the other parts of the project that we haven't heard about, as I've said, is this field-based collection of the biophysical and social science data relating to peat fires. And this information helps to support some and to explain some of the information that we get from the satellite imagery. And we've heard from some of the previous speakers how there's a lot of assumptions, and what we need is some ground verification of some of those results. And part of what I want to explain today is in support of this information. So what we did originally is to develop something called a fire scene evaluation. And when you're working with villages and in rural parts of Indonesia, it's very important to make sure that you're not being seen as investigating the fires with any intent on prosecution, because as you probably, many of you would know, lighting fires in Indonesia is seen to be quite illegal in most jurisdictions and under most circumstances. So in order to gain the information that we so desperately need, it's very important to explain to the communities and to the local government that we're not there as part of a prosecution process, but really to try and understand some of the science. And so what we've really done is focus these field activities on things that impact on fire on peatlands, and that's the fuel, we know the hydrology. We really wanted to understand a lot more about the peat fire itself and the behaviour of this, and a part of this was also vegetation monitoring. And then an important facet is to look at fire-related human actions and/or activities that are undertaken. So we first started way back in, I think, 2014, and the first lot of methods were really based on some of the questions that the fire investigators, such as Pak Bambang, do when they go out to investigate illegal activities. So these first lot of questions were really based on investigation of fires, because these sorts of questions had been undertaken for many, many years, and so we use that as the basis. But over the 4 years from 2014 to 2018, we refined these methodologies, and it basically then resulted in this fire scene evaluation manual, which is available, I think, on the IPB website. So this manual includes around 65 questions. It provides templates for field worksheets and descriptions and explanations for each question, so that we get comparable results between people, researchers, between sites and between fires. And that's really important. So originally we developed just a methodology, but then we found that we needed to put this explanation in related to the questions to make sure that the results were comparable across all these sites. One of the other things we found initially was that some of the answers from our field teams were left unanswered, and that's despite a large amount of time by myself and others working with the field teams in the field, working through each of these questions for the methodology and helping to refine the questions as we went. And we couldn't work this out. And so then what we decided after talking to the team in detail was to, they felt they didn't want to put answers down that may or may not be correct. And so what they did is left them blank, which wasn't really very helpful. So what I think we did then was to get them to put some confidence ratings on the answers to those questions, and then of course provide photo documentation so that we could later look at, when we were looking at the results, cross-check with some of the information. And that was a really big advance, I think, in the methodology to put these confidence ratings on the questions. So finally, what happened was the methodology or fire scene evaluation manual was developed, and it's in two parts. The first part is a general environmental set of questions and data collection, and the second one is all related to the peat. And our focus has been always on peat fires in the peatlands rather than the surface fires, but understanding that you need fairly hot and long-lived surface fires in order to get the peat to ignite. So how do we start? Well, we needed to find out where the fires were so we could go and look at them. And this was undertaken basically by two techniques, using the NASA satellite hotspot data. And then we've been very fortunate in the research area, which is really the Bos Moas in central Kalimantan Peat Dome, is that we were very well known to a lot of the communities there, and there's patrols during the fire months. So we were able to get communities to call in or send SMSs about the fire locations. So with this, coupled with the NOAA hotspot data, we're able to access fires relatively quickly, although you can see from the photo on the right-hand side that access is sometimes long and quite difficult. And then we face the question, we've got a small team, we've got multiple fires, particularly around October and September, October. Which fires were we going to focus on for the evaluation? So what we did then was we realized we wanted to focus on peat, so that was quite obvious. So if we thought that the fires were burning in peat, or we were told they were already into the peat, that was a high priority. We also gave priority to fires on deep peat. And the other thing was that we knew from past experience that if we had 2 or 3 fires burning over a certain area, that most of the medium and heavy fuels had already been consumed. Fine fuels are usually generated annually in the form of ferns, so that we were focusing on areas that had fewer than 3 burns, because we realized then that there was more heavy fuels available, and that's what we needed to ignite the peat. And as I said before, the focus was on peat fires. And then we wanted to look at different locations that had different environmental conditions, different peat types, had been burnt a number of times, and had different land use practices. So that then gave us an idea of where we should focus. So here's a bit of a summary of the sorts of questions and information that were recorded. One of the first things that was really important to do was to develop a coding system, because we wanted to put all this data into an Access database. And that meant needing to code things very, very well so that we could then understand differences between different fires in the same location. And when we came and had repeat visits, it was very important to be able to know what fires we were dealing with. So what we recorded is things such as the weather conditions. We looked at wind speed when we got to fires, wind direction, relative humidity, temperatures. In terms of the surface fires, we looked at things such as height of burn, scorch height, depth of the surface fuel that was burnt, and the vegetation type. So this was all together to gather information on the fire itself. And from that, we could then help to figure out, once we got enough of these samples, what were the conditions required for these surface fires to transition, if you like, into peat fires. And there was a little bit of information on fire damage. One of the other important things was to do a sketch map of the area. So it included land tenure and the data points where the fire was and had burnt. And that was then correlated with what we did later in terms of burn scars from satellite imagery. So these sketch maps were very important and helped to sort of substantiate some of the information we recorded from the satellite imagery. So phase 2 was really the fires into the peat. And here you can see that we looked at different peat ignition sources, the description, the weather conditions at the time, the fuel, the size, ignition potential, and then we did fairly in-depth studies of the fine, medium, and fuel loads, and I'll talk a little bit about that in a moment, because you really need those 3 types of fuel in order to get those surface fires to transition into the peatland. And once again, we looked at the human actions because we wanted to know whether the human inhabitants of the area utilize such things as the weather to either influence the severity of the fire or reduce the severity of the fire, and how the spread or whether they then modified the fire in some way. So all this was recorded. Now, I'll just go a little bit into some of the detail of the methods that we used in terms of fuel and water depth. And as you probably appreciate, these are the two drivers, or some of the current thinking is that these are the two drivers that determine whether we get peat fires or not. We undertook the surface fuels in the adjacent area to the fire because obviously it wasn't possible to look at pre-fire surface fuels. And we used this line intercept method, which is sort of a fairly well-known methodology in the fire world. And here we looked at these fine and medium and heavy fuels. At the same time, we put in two dip wells in front of the fire front and then behind the fire front, so that we could look at whether there was any impact of that water table on those fires. And that was, of course, measured using this blow straw method, which is quite well known throughout Indonesia. One of the things we've found now with fine fuels is that it's a really big factor in any of these surface fires, and so much so now that some of the more recent research has indicated that we should be actually subdividing our fine fuels into surface fine fuels, near surface fine fuels, and then suspended or fine fuels. And so this is very important because what happens is that you need the fine fuels in order to ignite the medium fuels, and then the medium-sized fuels then ignite the heavy fuels, and these then burn hot and for a longer period, which then determines whether the peat will ignite or not. So you can't go from having no fine or no medium-sized fuels straight to heavy fuels because they just won't ignite without the other two components. The next thing we had to do was to figure out what was the peat moisture content of the peat when the fire was burning. And here we developed, once again, some of these techniques we couldn't find too much in the literature, so we had to really rely on people such as the guys from the fire lab in the US that had done some work in peat. Kevin Ryan was very instrumental in helping us to figure out what sampling regime we would use in terms of the peat. So what we did here is we cut a section at the fire interface, perpendicular and approximately in an area of 50 centimeters by 50 centimeters. So halfway down and parallel to the fire interface, we used cores, which are about a 2 centimeter diameter cores to actually cut into the wall, or the peat wall, as you can see with those differences. And it's quite a simple process. Just used PVC piping, sharpened the end, and with measured notches on the end, and you can sample that peat quite easily and very accurately. What we did then is move down the profile at those 5, 10, 15, 25 centimeter intervals vertically until you could feel the peat was cool. And so the peat hadn't actually, or the heat hadn't actually transferred down through that peat. And so once we got to that cool zone, as I've indicated there, that we would stop sampling. So the samples were then weighed to a constant weight, reweighed, and then the moisture content percentage was then calculated. And you can see there on the photograph on the left, one of the team cutting into to the side of the trench that we've dug, and you can see the peat fire front there, right in front of the guys doing the work. So you have to get quite up close and personable to the peat, but nevertheless, it's possible to do it in relatively safely. The next part of the puzzle we wanted to understand was, what was the rate of spread? You know, do these peat fires really spread so quickly, and under what conditions? So here we developed a methodology by using steel rods, approximately a centimetre in diameter, and they were inserted into right at the burning face of the peat. Now, it was important to put an etch mark with a file into those rods, and they were inserted then into the level of the etch. And those rods were then placed about 40 centimetres apart. And so we had 3 lots of these to give us the sort of 3 replications, if you like. After about 24 hours, we came back and remeasured those rods. And so what we did is we leave them in the ground, and then, as you can see here, Thomas is measuring the distance from the rods, the original position of the rods, to the now peat surface, or the edge of where the peat is burning. And then, of course, because we've got the etch marks already on the rods, we could then get vertical measurements to determine the actual depth of burn. So it was a very useful and quite relatively easy technique to determine the rate of spread, and also to get very accurate records or measurements of depth of burn. And as you know, in the literature, this has been quite a difficult process, and there's been lots of estimates made based on probably not too many sample sizes, and I guess 1 or 2 vegetation types or conditions under which these were measured. So we found that this methodology was quite replicable. It was relatively easy to undertake, but it meant repeated visits to some of these burns, which in many cases are fairly isolated. As you know, there's been a huge number of estimates of volumes of peat lost, and then conversions to carbon. And a lot of these were done with 1 or 2 measurements, not very well replicated, and under all sorts of conditions. And one of the things we realized was that there hasn't been any real accurate measurements taken. And for those of you who work in peat and on peat fires would realize that peat doesn't burn uniformly through the landscape. Even in an area of 1 square metre, you can get parts of that peat that's not burnt. You can get other parts that are very deeply burnt. And so it took us a while to figure out a methodology to actually determine what we call this loss of peat. And it's really based on trying to get an estimate of the surface of the peat before burning, and then coming back and putting down a quadrat, if you like, as you see there, and putting it in the exact position at the same height, and then taking the remeasurement to then get to work out what the loss is. So here we've developed this mobile square quadrat, if you like, where the individual quadrats are about 20 centimetres by 20 centimetres. So this gives us an intersection, or it gives us about 81 intersection points over an area of 160 centimetre sort of square quadrat. And it's important, as you'll see in the diagram, not to make the quadrat or the square too big, because you have to lean across the square in order to measure the depth at the centre. So the size of the square is really limited by 1 person's arm length. So we took all this into consideration when we were designing the quadrat to make it practical and therefore accurate. So what you get from this is really, at each intersection of those squares, you get a distance based on the X, Y. In other words, as you can see from that top diagram, one of the axes is X, the other one's Y, and then the depth is, the X is Y, and then the depth is really the Z measurement. So once the fire has gone, we then re-establish that square and insert it exactly in the same position at the same height as what we did pre-burn, and then we remeasure those X, Y, and Z coordinates for each of the 81 intersect points. And once we have that, we've got a mathematical equation to convert that into determining the volume, or the peat volume that's been lost during the fires. And of course, with this method, it takes into consideration the areas that unburnt, and that's really important so that we don't overestimate or even underestimate the volume of peat lost. And so while these are very small quadrats, we realize that by doing a large number of them in different peat types under different conditions, we'll gradually build up quite an understanding of what happens in these peatlands, and that once again can reinforce what we're getting from some of the satellite imagery and some of the burn scar analysis that's been done. In order to support these field activities and to I guess facilitate this field decision making, what we've developed, or Laura Graham has developed in this case, is a field activity flow diagram. And I think this will help a lot of you to understand the process of what I've described and some of those measurements and questions that we need in the fire scene evaluation. So once again, we do the fire reporting, and here the fire's reported. We cross-check between the different sources and we decide which fires we will go to. The next stage is in actually getting to the fire, conducting that fire scene evaluation form, which is the part 1, which is the surface fires predominantly. If it's a peat fire, we'll keep going. And as you can see there, if it's not a peat fire, we will stop the evaluation because the focus is really on the peat. We'll complete the second part of the evaluation, conduct fuel load assessments, etc. If it's possible to return to those peat fires and do the rest of the measurements, we will. But if we can't, we will just stop there and just finish off with the fuel loads. But what we'd like to do is conduct then the water table depth measurements, the peat moisture content at the peat fire interface assessment, and then undertake the rate of spread assessments. And once again, is it possible to return to the site in several days? If the answer's yes, we will do that, and if not, we can't. But one of the things we'd like to do is to try and get ahead of that fire front so that we can undertake this loss of the peat lost from those fires and determine the volume of peat. So that's sort of the process that we go through in order to complete that fire evaluation process. So as you can see, it's not always possible to do all of those measurements and conduct all of those research, undertake those research questions, but there are stop-go, as you can see, stop-go signals through that process. And that's important because sometimes it's just not possible to undertake some of the other work. And I thought it'd be useful to present this so that you'd realise that in not all circumstances can all of those studies be undertaken. Now, as you've probably gathered, undertaking these measurements, 65 questions, all of these different moisture contents, fuel loads, rate of spread, we generate, and taking photos at all of these points, we generate an enormous amount of information and data. And things such as the tools such as Excel just won't be sufficient. So what we've done is Pavla Graham, a database manager from the UK, has kindly developed this Access database, with the user interface and analysis capabilities that has enabled us to not only input the data, but to actually facilitate export queries. And these are all based on combinations of the environmental data, and we can do this over both space and time. And so that's a really important part of, as you know, any research is to be able to capture the data, store it safely, and then to be able to export queries and to, in order to analyze the data so that you can then produce the scientific output that's required. So what we've just felt that the application of this methodology is that it improves our understanding and calculation of the tropical peat and peat fire behaviour. We found that when we did this, there wasn't much information in the literature or generally known about peat fire behaviour. And so this, this methodology that we've developed documents it very well in a very objective way. The data can be coupled with other components such as the smoke analysis of burning peat and the work that, and complement the work that Bob and his team are doing, and particularly in the generation of these emission factors and emissions models for the peatland. They provide a calibration and verification tools for the remotely sensed data that we heard about in the webinar 1 and 2, and more. And I think importantly, from a ground and research point of view, these methods can be applied elsewhere, and they've provided a really useful, I think, standard operating procedures for monitoring tropical peat fire on the ground. So with that, Indra, I'll stop there, and we'll hand over to you for the next speaker.
Okay, thank you so much, Graham. Nice talk from you. So, ladies and gentlemen, so now we have 2 speakers already. From Bob, we got the brief explanation on how dangerous the peat fire are, and some measurement and observation have been conducted of smoke samples from various parts of Indonesia, like in Sumatra and Kalimantan, and also from the surrounding. And from Pak Graham, we learned how the project tried to sort out the evidence of the peat fire and the characteristics of the peat fire. But still hold on the questions. So please, if you have a question, you can write in the chat room, and we will deliver your question and ask for the answer from the speakers. But we are going to have our third speakers. Pak Bambang will talk on how to implement this result of the smoke and haze for the Indonesian. Pak Bambang, time is yours.
Thank you, Indra. I will share the presentation today, and then in the beginning, I will show you 1 or 2 video about what, how look like actually the peat fires, or maybe the mix between peat fire and surface, and then how actually the people going on in the ground. So I'll share my page screen here. I think you can see, yeah, my presentation. Okay, this is a title asked by the steering committee to talk that I will discuss this with you during my presentation, and then we will start with the video. This video occurs in the Peat area in 2019, where the burn area is about 2,000 hectares. You can see from here the smokes. There is also flaming here, and then this is what I said, the mix between surface and also peat, because here it's not all blending, yeah, but also have a smokes there. Also the different color will show it. You see how worse this fire here. See, this is only in not in one side in here, but also it may be occur in other places. Okay, then we move with the other ones. You can see the smoke is mostly white here. And you see how the people try to stop the fire here on the ground. This is in the Peat area located in South Sumatra. You can see from here, this is also flaming. The smoke here, we are lucky this year it's not so much like it happened before in 2019. Because sometimes, to fight the peat fire or the surface peat on fire on peat is not easy, you see. And then from here, can you see it clearly? This is a dry fuel, and this is the flaming occur here, and the other one is burned already, and mostly you can see they produce smoke here and still working. So from here also you can see on the surface is also there's many vegetation, dry and still green, that will impact to the performance of combustion. And then this is the result. This is also on Peat. This is in Central Kalimantan. And then from the view, we can see how the smoke transferred to other places that can be monitored. This is in Pulau Rupat, in Bengkalis. And then the question is how to calculate the greenhouse gases. I think Bob already good explanation regarding how to calculate or to measure greenhouse gas in the field. Yeah, this is a part of what we are doing in Central Kalimantan 2015. See, this system, this is canisters, this is CTIR that mentioned by Bob. This is what we did last year in South Sumatra, Jambi, and also Riau. You can see this the investigators, principal Mark is already here, and this is Bu Ati and Indra, and you can see here when we are talking about peat fires, and the samples also taken peat here. So because if you missed with the definition of peat fire and surface fire and peat, and then the result is totally different. So you see why then this is Ati looking the sample here. It's not here, for instance, like that. This is here. So this is what we would like to get the good result, that we were talking about peat fires and also the product sample, and then this is come directly from peat fires, not a mix with the surface fire on peat. This is the same, I think, what Bob mentioned before about the canisters. But the question again, how if we cannot directly calculate in the field of the measures? It means that we use the equation. Yeah, this is result. This is mentioned by Bob before. And then from the results, finally, is also mentioned by Bob. We finally found that there is overestimate of the gases. For instance, like CO2 is 8% overestimate, and methane 55%, and also NO3 is 86% overestimate. and then CO you should plus 39%. So it's mean that this result actually should be used to revise to the IPCC equation for CO2, methane, and others. Because from new emission factor, we finally recognize that is something is going in there, because the CO2, methane, and OH3 is overestimated. Even for NH3, overestimated for the more than 86%. So then, what we are talking now is when there is no, we cannot directly calculate greenhouse gas or Smith in the field. To IPCC 2014 use this equation. We also used by Indonesian government to calculate the emission here to monitor, to calculate CO2 and non-CO2. From here, that I would like to focusing is in here, because they put the combustion factor dimension list, because the others I think is almost the same, but sometimes also the value is different, because the area is also different, like mentioned by Bob. So we are talking in Sumatra, then use the Sumatra, but we have to Kalimantan, use the Kalimantan. But the problem is sometimes is that still used until today is this one, is combustion factor. Because we use this IPCC 2014, they calculate that this L fires, it's mean that they will be calculated between total area burned annually, and then times the mass of fuel available for combustions, and then combustion factor, dimension list, and finally is the emission factor for each gases. And also from here, using the IPCC 2013, also Indonesian National Carbon Accounting System is also used this one. You can see here, carbon combustion factor is still used here. See? And this is for Peat, also almost the same. This is I quoted from Budiarto 2019, where this is here, you can see clearly that combustion factor on Peat is 1. I think this is one good debate. Why then the put combustion factor 1 for Peat? So we are talking peat fires, and also, but the other one is surface fire on peat, especially on CF, is totally different. Because when you talk about combustion factors, it means that this is the same with the burn fuels divided to the fuel that's not burned. So if you have a combustion factor 1, it means that your pool totally burns, nothing left. How could it be? This might be only for like alang-alang. If you have 100 grams of dry alang-alang and burn totally, there's nothing left, then you got 1 for this combustion factor. But the question how it works for the peat, because we cannot get the dry peat. So is there any reason that you can put combustion factor 1 there? This is the question, right? So this is the parameter used when using that formula for IPCC. Again, they use this, for instance, like burn depth is 18 for first fire, second fire is 11, third fire, and then what I would like to focus is in here. They use 1 as the formula or the value there. Then they put in the equations, right? So this is the other factor they use for emission factors, like I mentioned also by Bob before. When you use CO2, which one they can use? For instance, like Christian's in 2004 publication, and also Coaster with the same, and then Stockwell. So so this data is already that results is from research, and with also difference. Like this is from a laboratory. There's also from institute like we did in Central Kalimantan, and also from laboratory, etc. So they have different kind of result here. And of course, finally, because of the characteristic of peat also different, and mean here also the peat the burn in the book density. This is finally we got the result. Like from page they mentioned about 0.51. Bullhorn is 0.3, Usop etc. 0.35, and Stockwell is 0.34, and also the others. This is from bulk density. So even the BRG, I mean, this is the button restorasi gambut. They use also the combustion factor for peat is 1. Yeah, this is also one reason. So this is just one example. When we are talking about fire in peatland, there will be two possibility of fire occur there. One is what I said before, is surface fire on peat here. Because what? Because the peat is already wet because of waters, because of good canal blocking, etc. So it's mean that the fire occur only in surface. So then this is like I show you on a video before, that how Bu Ati, for instance, looking for the site that where the actually peat burn. Because when you take a sample here in peat fires and surface fire on peat, then the result will be different. Because here is surface fire on peat, like you see in my video, but here is a peat fire. So it's actually, this is a difference, right? So this is to make easy. I took it from Google, something like that. This is the grounds, you see, because gas or smokes is to be like colors like this, because this is not affected by the wind, etc. But here, the red is different. This is flaming. In here, we cross this is smoldering, but this is flaming. Yeah. And then this is here the sample. Yeah. Here, when we have here in the smoldering, when the fires going down, and then this is below the pit surface, something like that. So like this one, yeah, this is a surface. This is outwards, yeah. So here, because of what? Because of also covered by waters and wet. So the surface is sometimes not easy to burn. So it means that when you took samples, smokes here, and also here, of course, there will be a different result. Like this here, it's easily. This is a surface, and then bird here, smolderings. And sometimes the result is we don't know exactly where actually the fire occurs, because only smokes. So be careful when you're going to this area, because they will attack maybe your food, something like that. So this is just mentioned that when the peat fire occurs, yeah, this is below the ground. They go through this what's the goodest route, yeah. So I will ask you, and we'll discuss with you how this CF1 comes. This is from IPCC. This is the coordinating lead authors with so many experts, yeah, excellent experts. And then one is the one issue is that they mentioned when you're talking about the emission factors that they mentioned, yeah, for tier 1 for organic soil fires, the default combustion factor is 1.0. Since the assumption is that all will combusted. This is from Bob papers. So then from here, from the result, then I communicate to Bob Nicholson through the email, because they mentioned about his paper here that used by IPCC that mentioned the CF is the same ones. So this is the commenter made by Bob. Sorry, Bob, I put you here because I mentioned that this is impossible to get combustion factor for peat is 1 because they're already covered by waters. It's very hard to get once. So Bob's answer is that yes, you're right. Combustion factor is less than 1 for peatland, where peatland includes some wet peat, some mineral soil mix in some pocket that does not burn. Then Bob mentioned also that it usually get mass of peat burn without even using combustion factor. This is a question made by Bob. Yeah, so means that this is area burn times depth of peat burn, and then times peat bulk density, and then this is the emission. mass of oil burns times emission factors. Then from here, we know that no need for percent of combustion factor. And the other point, I asked also about his paper. And his Bob answer, I don't remember discussing combustion factor in 97 papers. And I looked at the papers, I did not see any discussion of that. I converted the file you sent to settable amount document and set on combustion finds many cases. So the set is working, but a set on combustion factor does not find any cases at all. So somebody made mistake when they quote me. So it means that in the Bob papers 1997, there is even no words of combustion factors. So how the people could quoted his paper mentioned about CF, the same with ones. This is a recommendation by Bob that if you would like to calculate using what's combustion factor, there is possibility here. But you see, the combustion factor must be taken from laboratory, not by feeling. Yeah, and then this is only one example. What they mentioned by also by Bob. This is paper made by Akagi, etc. et al. And then from here we know on Finland there is no combustion factors. Yeah. So of course later on there is separate papers using the combustion factor. But the problem is how we can put the ones in the formula as the combustion factor. And then actually this is we would like to to share with you. To forget it about combustion factors, then we use this factor equation. Yeah, this is without combustion factor, but we calculate that mentioned by Bob. Or maybe you can use the MCE because many papers or many results is using MCE. So this is our recommendation is using this emission factors that actually are taken from our papers in 2016 based on our fifth recommendation, build result. And then this is the conclusion. Number one, greenhouse gas calculating use IPC equation. We use CF that is not represent the real condition should be revised. This is what before. How could you put the CF1 on the peat? Because when peat burns, we cannot get the data or result all totally peat burn. Not because it's still unburned there, because the peat covered with water. Even now, there's rewetting there. Is there possibility to get CF1? I don't think so. Second, quoting 1997 Bob paper about CF, which actually was not written, but then directly translated into the IPC equation as CF by the name of it, and since should be revised or removed. Yeah, and the last, it is suggested not to use old IPC equation. Yeah, but then starting to use the new greenhouse calculation based on the scientific data. So this is what I saw you before that what's the misunderstanding about when they quote the IPCCs with the CF the same one, that finally we got the result that in the Bob paper there is no CF the same with ones. So it's if you still use that ones, so you should modify it. Means that IPCC is not ones. So you the papers published that can be used should be well recognized, or otherwise forget it about the CF, but use change like what I saw you before, or using the MCE. I think that's all I would like to say for you. Thank you very much.
Okay, thank you very much, Pak Bambang. There is so much debatable here from the combustion factor. I think in the discussion later we will hear what will say by Bob of this controversy. But before that, I think we have to learn what is the government view of point of this smoke issue from Pak Isar. Pak Isar Albar, time is yours.
Thank you, Pak Indra. Can you see my share screen?
Yes,
Okay.
absolutely.
Okay. Good morning and good day and also good night for some of you over there. I would like to thank Professor Bambang Hero Saharjo and Professor Marco Kren for inviting me in this important webinar, Peat Fire and Smoke. I also send my best regards to our resources person, Professor Bob Carlson, Associate Professor Graham Applegate, as well as to all attendees. Thanks also to our today's MC, Bu Ati, and moderator, Dr. Indra. It's an honor for me to be here today. I'm going to share brief information about the challenges and opportunities for fire management in Indonesia, particularly in how science supporting fire preventions. So this is my outline of presentations. I would like to begin my presentation with the historical figures of active fire, also known as hotspots, in Indonesia during 2015 to 2020. We all know that 2015 is the tremendous fire seasons, not only in Indonesia, but also in many parts of the world. Moody's detected almost 180,000 of active fire in 2015, and significantly dropped to 24,000 and almost 80,000 in 2016 and 2017 consecutively, decreasing almost 90%. So, however, last year, the active fire detected 90,000, which is half of 2015 active fire. This year, as of October, I think the active fire detected only about 7,000. All data is for all level of confidence. Besides the active fire, we also noted that burn area in Indonesia, particularly for the last 2 decades, both in mineral and peatland. This graph showing that during 2006, 2014, 2015, and last year, were among the largest burn area with number of variation of emission from peat fire, as shown in the gray line. In this year, 2020, the emission from land and forest fire around 36 million tons CO2 equivalent. This is the smoke in Jambi province captured by Sentinel on September 21st last year, 2019. And the left picture describing the smoke from the ground at the same sites. So you can see. Yes?
Sorry, your slide is not changes.
Uh-oh.
Yeah, it's still in the first slide.
Uh-oh.
Yeah, still the title.
Okay, wait, I'll check. Okay, wait.
Yeah, that's it now, Isra. Looks pretty good.
Okay now?
Yeah, but needs to be in slide presentation mode, I
Yes.
think.
So let me check to the second. So you
Okay,
can see the
it works.
one?
Yeah,
Oh,
that's
okay, sorry.
okay.
Sorry for the one with the network. So you show this this slide before. I mentioned about this active fire in Indonesia in 2015 to 2020. And you can see here in 2015, there's the highest number of hotspots, and it's decreasing to in the next year, 2016 and 2017. And this year, I think we only have 7,000 hotspots. All is in confidence level, 0 to 100. So this is the burn area beside the active fire. We also noted the burn area in Indonesia in from 2000 to 2020. And this graph showing that the during 2006 year, and then 2014, 2015, and 2016 is the largest burn area with the number of variation of emissions from peat fire, as shown in the green line here. So the smoke in Jambi province last year, September 21st, is captured by a Sentinel, and the left picture describing the smoke from the ground at the same site. Next slide is the NASA's Aqua satellite, also captured the smoke from fire surrounding South Central Kalimantan on September 14 last year, just 1 week from Jambi smoke at the previous slide. Then September 15 last year also, the only on Landsat 8 acquired this image which show fires burning as well as smoke in several areas in South Central Kalimantan here. You can see the active fire here. We understand that the fire management consists of three aspects. First, prevention, and then suppression, and then post-fire, where prevention is the most important one. We have regulation in place, early warning and early detection system, supported by the integrated patrol and ground checking at field, while campaign and capacity building should also be improved, and enhancing skill and knowledge on land clearing without burning, we call it the PLTB, for local people. There are several data and information that we use in early warning system, fire danger rating system that we developed since 2002, where we can have information at national and provincial level. Here, for example, here is South Sumatra province. For all FDRS indexes, such as fine fuel moisture code, DAF moisture code, draft code, build-up index, initial spread index, and of course, fire weather index. This FDRS run by BMKG, Meteorology, Climatology, and Geophysics Agency, provides a 7 days prediction. That information is useful for us to make a decision for preparing and mobilizing resources to conduct ground operation. So you can see here on the top is for the whole Indonesia, and the bottom is only for the South Sumatra. And then you can see also here, today is December 15, and this data showing December 18 until December 21st. The second application is for forest and land fire. We call it API Khatulistiwa. It's application of forest fire and land cover early warning based on ASEAN regional hotspot and climate, where we can have prediction for next 6 months. So we can call it long lead predictions. This figure showing the climate index for suitability of hotspot occurrences for January, February, March, and April 2021, which are also developed by BMKG. We also put attention on El Nino southern oscillations indicator from weather or climate agencies to get well prepared if El Nino phenomenon and long dry season occur in relation to land and forest fire potential. So this graph predicted that up to May 2021, there will be no El Nino, but perhaps La Nina with weak to moderate level. If early warning system gave us information on potential fire occurrences, the early detection systems provide us with near real-time fire occurrences. Since 1997, we developed and improved our early detection called SIPONGI, where we employ NOAA and then Terra Aqua, SNPP, and now Landsat 8 to detect active fire. Our SIPONGI application now running for UN Public Service Awards, which will be announced, I think, next June. And additionally, in the right side, Himawari satellite captured by BMKG also completed us with daily smoke distribution and geo-hotspot. So this is the early detection system that we have since last year, 2019. In order to enhance our detection system, we established thermal camera or CCTV in 15 locations, particularly in Sumatra and Kalimantan. You can see here in Sumatra, there's a couple CCTV, and also in Kalimantan. And as drone also become more easily to operate, our fire brigades Manggalakini at the field also use them to patrol and estimate burn area locally. This has come to important part of our discussion today, considering that a fire ignited at the site level village. We classify fire vulnerability villages in 20 provinces based on some criteria such as hotspot and peat distributions, land cover, area function, elevation, slope, a fire area in during 2015 until 2017, and found that 4,140 villages are prone to fire, where 52% are found in Sumatra and 44% found in Kalimantan. We categorize the villages into 4 classes of vulnerability: low, moderate, high, and extreme or very high. And you can see also here the gray color here in eastern part of Sumatra, and then western part of Kalimantan, West Kalimantan, and also in South Kalimantan. That's a peatland. And here the South Sumatra, where we can discuss more about this area later on. So this is the fire vulnerability in South Sumatra. I took this province as an example, where I spent 1.5 years there. This province has 3 million hectares of forest, 1.3 million hectares of peatland area that are susceptible to fire, with more than 3,000 of villages. 88% are low, 2% are moderate, 4% are high, and 6% are extreme. The map showing all villages in South Sumatra, where light blue is low, light green is moderate, and orange here is high, and light red is extreme. The gray at background is peatland. You can see here in the top, in the north part of Sumatra, South Sumatra. You may see also the most extreme class located at the peatland area here. We also analyzed the active fire during last 6 years on the vulnerability area. In 2015, active fire clearly can be seen in extreme class and peatland area. In 2016 to 2018, active fire decreasing significantly, but still can be seen also at extreme class and peatland area. Last year, the active fire had some pattern with 2015. Most fire found at extreme class and peatland area, mainly in north here. This is a Banyuasin Regency, and western, this is Ogan Komering Ilir Regency. Another study that we did is analyzing the burn area, compare with fire vulnerability and peatland location, both in El Nino and no El Nino years. In 2015 here, El Nino year, in line with the active fire, 46% of burn area occur in peatland area with its extreme class. So we know now that the most fire in South Sumatra occurs in peatland area and also in a very high vulnerability to fire. To prevent the fire occurrences, since 2016, we developed integrated patrol at those areas. This year, we did in 43 post command at village as shown here on the map, the blue color. So this is the post command for the integrated patrol. This year, I think we did more than this for the whole Indonesia, almost 300 post command. Additionally, we also developed fire care community or Masyarakat Peduli Api as a frontliner at their villages. The climate village program or program Kampung Iklim as a joint adaptation and mitigation activities also introduced in South Sumatra, and since 2012, there are 100 villages and already registered. The integrated patrol consists of a team, Manggalagni, and then army, police, and then a community or a MPA. The composition of this team is flexible according to the conditions and needs in the field. Each integrated patrol post can reach 2 until 3 villages prone to forest and land fire. This year, Integrated patrols have been carried out in 333 village posts in Sumatra and Kalimantan, reaching almost 1,000 villages. This is the Fire Brigades Manggalagni, our resources for the whole Indonesia, which was established in 2002 in fire-prone provinces and 21 local fire centers. But nowadays, it has 34 local fire centers in 11 fire-prone provinces in Sumatra, Kalimantan, and Sulawesi, with total about 1,875 personnel. Additionally, more than 11,000 personnel fire care community also registered. As mandated in President Instruction number 3, year of 2020, there are 26 ministerial agencies, including governor and head regency, bupati or mayor, involved in fire management, head by a coordinating minister for politics, law, and security. So we have for these all stakeholders will also contribute in decreasing the land and forest fire in Indonesia. So this is my last slide with a special message, how to connect the science and the fire management. To deal with the fire management, we need to have a science base. The IPB, Uni Maryland, NASA Tropical Peat Fire Research is one of the excellent example where I also involved with. To me, my colleagues, if I get lost in decision-making process, the science and scientists are the place where I return. So that's my my principle. So the list of these activities, the emission factor, burn area, and so on, is the project by IPB and Maryland, supported by NASA. So I think that's all my presentation today. I hope my brief presentation could give another perspective and update to all stakeholders that the Ministry of Environment and Forestry emphasize on fire prevention in fire management, and hope science will contribute much in policy decision-making process. Thank you for your attention. Stay safe and healthy. Back to you, Pak Indra.
Okay. Thank you so much, Pak Isar. There's a nice talk about the what is the condition of the fires in Indonesia recently, and how to bridge the science to the fire. And also, I'm sorry for some noises during the presentation of Pak Isar, because there's an announcement of the one of your friends has passed away, Pak Isar. I'm sorry for that.
Thanks.
So we are now going to the discussion part. There's some question from the chat room, but before that, I think I wanna hear about you, Pak Isar, for this the critical question from Pak Bambang for the combustion factor of 1. Do you have any idea, Pak Isar?
Yes, we discussed about this a lot with Pak Bambang also, and I also mentioned to my colleagues in the Ministry of Environment and Forestry, even to our DG, and our DG already make a note to my colleagues also here. Please be consider, and also what do you call it, to improve the combustion factor, because it should be less than 1, as mentioned in some reference, including the IPCC. So I think this is our excellent time also. We have to engage with all stakeholders, especially for the one who get the connection to the IPCC, and then ask them, to revise or to whatever, to revise the combustion factor in IPC. That's our idea, and also my DG. Thank you, Pak Indra.
Okay, thank you, Pak Isar. Do you have any comment on this, Bob? Because some of these guys is referred to your paper.
Yeah, I think that Bambang's presentation showed the correct equation. can use combustion factor or you cannot use combustion factor, but if you use both methods right, you should get the same answer. So for instance, if the peat is 1 meter deep, but it only burned down for 34 centimeters, what you would do is you could say the mass of fuel, you would calculate it as using the full meter depth, but then use a combustion factor of 0.34 to account for that it didn't all burn. Or you can just skip the combustion factor and calculate the volume of peat that burned by using 34 centimeters directly. So I don't know if that's making sense, but I see Bambang presented it correctly in his talk. And so I think that you guys have it worked out correctly, but I'm happy to comment more offline. It's a little bit difficult to, it'd be easier with a blackboard to go through the steps or something, but not so much just talking equations in the air, but it's well understood.
Bob, just to comment on that, I sort of agreed with everything said, except that I'm not sure where you get the idea of 32 or 31 or 15 centimeters peat depth, because at the moment, that's one of the big issues is we don't have very good methods for calculating peat depth and volume of peat consumed over large areas.
That's so
correct. You might get all the formulas right, but one of the key ingredients is the peat depth or peat volume.
Right. So I think with the data that you've collected and with the data that's published, one would assess what's the best average value and apply an uncertainty to that. So for instance, when I said 34, I just made that number up because the sites we sampled in 2015, they measured on the edge of the where the burn was progressing with a tape measure. And they saw that like the little cliff on average was about 34 centimeters high. But that had an uncertainty of plus or minus 12. And so if you have 100 or 200 data points from your work that suggest a different number is better, then I would definitely agree, use that. It is a very difficult thing to measure, and Mark would weigh in about the attempts to measure that using the LiDAR from the aircraft, which is yet another approach. So that's a big source of uncertainty, but the more data we get, there's more hope to converge on a reasonable average number. I don't think we'll ever be able to do it at high resolution where we compute the burn depth, point by point for every fire. But we may do something where we say the burn depth increases as the dry season increases, right? So it may be closer to 10 centimeters in August and closer to 30 in November, kind of thing like that, if your research supports that. As the water table drops, the burn depth increase.
Yeah, with this kind of conversation, Laura and I had the same discussion, like combustion factor. Depends how you use it. I mean, if you're going to be just describing what happens in a particular fuel at a particular site, you need combustion factor to get it right. If you're going to estimate over a larger area, you can just scale it back and pretend, it was 100% of a lesser amount. The other problem that we get into, as Bob is mentioning, we're talking about you can make a blanket average for an area, but you lose any spatial ability to say where it happened. One of the other problems we're having now is, as with Amanda's work shows, is that bulk density is very variable. So the same depth of peat in different areas will have different amounts of carbon release. So if, it's all a matter of what you want. If you just want some global number for Kalimantan, you can kind of hand wave a bit and say, at an average depth of whatever, 5 centimeters, we can think it was 100% combustion factor. But if you want to know what happened in Mawas, especially near the canals, you'd have to be much more exact. You'd have to account for the disturbance history, so some estimate of the bulk density of the peat. We'd want better data on the depth of burns.
Mm-hmm.
Right. So it all depends on the scale of your assessment. If you're doing a large scale assessment and nationwide calculation, you probably have to use average values. But definitely if you want to do like a case study of what happened at one village and, how much smoke did the people in this village get exposed to, then you could probably do a higher resolution calculation. Everyone has a limited bandwidth, right? There's so much data you can put into a model before you can't, finish on time. So
Yeah.
so I agree. There's lots of different levels of detail that could be appropriate for different skills.
Okay, thank you so much for the discussion, Bob, Mark, and Graham. I think there is some suggestion from Pak Gusti Ansari that we can actually contribute to the revised IPCC report. Can you say something about this, Pak Gusti? Pak Gusti, are you there? Pak Gusti.
Yes, thank you.
Okay.
Okay. By me, right now the IPCC open for review for second order draft for IPCC IR6, not really for greenhouse gas inventory. So, but we need to look at the chapters. Maybe you could find the section discussing this issue. Maybe in the in one of the chapter about the climate development pathways. Maybe there is an issue there that we could insert this a new finding, because IPCC also need the peer review literatures, in order to contribute. So I encourage Indonesian participant maybe to be reviewers, because only a few numbers of Indonesians usually contribute to the IPCC report. Thank you, Pak Irianto, for asking.
Okay, thank you, Pak Gusti.
Yeah, you just use the link that I share. That you can look at and then choose the chapters you would like to be in. Thank you. Yeah.
Okay, thank you, Pak Gusti. So you can find the link that Pak Gusti want to share in the chat room. Pak Bambang, what do you think about this to contribute to revise the IPCC report? Because I think we have to revise this IPCC, I think, because they use the CF of one is maybe is questionable.
Yeah, actually, after our papers published in 2016, and after we present it in Texas with you, Indra, and also I went to UK, presented in front of the session page, that I said that something should be done for these ones, and I communicate with the ministers, and then straight away, then I've been asked to hearing with the newspaper, etc. So this has become one of the issue. So unfortunately, we cannot directly send the argument, because according to regulation, I'm like what Professor Gusti mentions, we should send the comment through the Indonesian expert who become of IPCC team, something like that. So actually, I sent already to two professor, Prof. Edwin Aldrian and Professor Pamudin, but until today, it's nothing. So I think suggestion made by Pak Gusti, I think it's a good idea. We should through that way, using this revised argument, because you see, if we directly use the CFs the same with ones, it's mean that we directly agree to increase our own greenhouse gas at least 3% to 40%. That actually is not like that if we are depend on our result of the research. Actually, this also mentioned by previous speakers. So yeah, I think we should use this one, and then hopefully there is still open for sending the argument. That's it, Indra. Thank you.
Okay. Thank you, Pak Bambang. Pak Isa, can you facilitate this?
Yes, I think this is also our concern, and we know, as I mentioned before, that we need also the science and then become the policy, and this issue also, raised in our ministerial, and I would like to check again with my colleagues here how about the progress of this, because we can also convey this message to Pak Fahmudin Agus and also for Pak Elvian, and say something as a connection to the IPCC. So that's what we will do, I think.
Okay, thank you so much. I think this one is quite one of the important results from this webinar, I think. Hopefully we can contribute to the efficacy to revise the number and so on. So we are going to the discussion part. There is a question also from Pak Gusti. This is for Pak Graham and also Pak Bambang. Burn depth measurement is a challenge. I would like to ask Pak Graham and Pak Bambang, you have a simple formula to estimate the burn pit depth, perhaps based on fire intensity and the fire duration. Pak Graham, I think you can answer this first.
Thanks, Indra. One of the reasons we haven't got a formula at the moment is we really don't understand the process very well, and so these measurements that we're taking are a way of observing some of the issues that we see while we're doing these measurements, and of course it's not just the intensity of the surface fires, but what we find is that the peat also contains huge fuel loads of dead branches and logs, etc., etc. So if there's a large amount of these in the near surface, then the peat tends to ignite these, and then these themselves then are a huge source of energy, and that drives the peat fire. The other thing is we find wind is a huge factor. If you've got wind hitting the face of the peat, then it tends to blow it, burn it deeper, and these are, and then water table depth, etc., is just another factor that will influence the depth. So at this stage, I think we just haven't got enough data points to actually make some correlations and so develop an equation at this stage.
Okay, thank you so much, Graham. Pak Bambang?
Yeah, as you know, I agree what the mentioned by Bob, Mark, and also Graham, that every burn area, or especially on peat, they have their own characteristics. So sometimes it's not easy to make any generalization, especially when we are investigating case by case. So what I'm doing is that if you would like to use the value or parameters or result, you should be one packet. So it means that if you use burn depth in this area, that you use also the other parameters where as produced from these papers. You can use, for instance, like the burn depth here, and you use the others MCE. So because every research will have their own result. So this is the reason why I make a recommendation based on our research, for instance, in Central Kalimantan, because there is clear how big the pit depth there and how big the MCE and also the emission factors, etc. So this is in focusing all those in one area. But you cannot use, for instance, like for burn depth, you use this, but the other MC used from other researchers, because like mentioned by Bob also already, you have different type. You cannot mention like you are used in this expert. Finally, we got result. This is from Kalimantan, but the others, we use the other parameters that we actually recognize this come from Sumatra. I think because the result, the impact will not good. So I recommendation to make it based on our whole research. So from there we guarantee that all we did we know, and also in the same area. You cannot use with like I mentioned your parameters there. It took from here, and this one is here. No, the real result will be very not good, you see, or maybe biased. That's my comment in that.
Okay, thank you, Pak Bambang, for the brief answer of the question from Pak Gusti. And I think we can move to the other question. This is also from Pak Gusti, but this is for Pak Bob. It is very impressive results, Bob. I have a basic question about the pollution of the peat fires. How long do the toxic chemicals of burnt peat reside in the smoke and haze? Second, how many kilometers do the toxic has transported?
So two things happen to the chemicals that are in the smoke. They mix with the clean air or the other air, which could be smoke, but usually they decrease in concentration because of dilution. And then also sometimes they react chemically with other things in the smoke and go away slowly or quickly in some cases. So for every compound, it's different. And some compounds are both destroyed and made. So formaldehyde, for instance, lasts a long time in the smoke plume because there are new sources of formaldehyde from the chemistry in the smoke plume. Ozone gets worse as you go further downwind because it gets made in the plume. But other things like furan or benzene goes away pretty quickly. What we did was we in our 2016 paper, we looked at how much particulate matter, how the gases ratio to particulate matter was, and what was the actual concentration of particulate matter in Palangkaraya, according to the airport smoke monitor. And from those two data points, we estimated that formaldehyde is most likely the most dangerous smoke chemical that people were exposed to in Palangkaraya. But you know, the exposure to smoke is a very inexact science because it's usually there's limits that you're not supposed to exceed that are based on breathing that's level 8 hours a day for your whole life for 20 years. Those are called the long-term exposure limits. And of course, with the smoke, it's, you know, it's clean part of the year and dirty part of the year. There's other types of studies where they look at what's in people's blood to see how much they've been impacted by the smoke. And that's something I thought would be a really great, another form of research to start doing in places where people are exposed to smoke. But there hasn't been any of that yet in Indonesia. And I'm not sure if I'm getting to the question, so I'll stop there for a minute and see if that helps. I don't know.
Mm-hmm. Okay, thank you, Bob. Pak Gusti, do you have any comments on the answer from Pak Graham, Pak Bambang, and Bob?
So far, it's fine with me. Thank you very much for the answer. It's clear enough. Yeah, I enjoyed it. Very good.
Okay, thank you so much, Pak Gusti. And this was the other one is from Pak Sutomo. This from Lipi to Bob and Graham. is there a significant correlation between peat fires and the ENSO dynamic in insular Southeast Asia? Maybe Bob first, please.
Oh, okay. I think actually Israr's talk showed that really well. You saw a lot more hotspots in 2015 when it was a big El Nino, and I'm sure Graham agrees, but I'll let him comment also if he has extra to add to
that. Well, as Bob said, ISRA's hotspot data is very, very clear. I guess one of the things that is a little bit unclear is the hotspot data in 2019. And wasn't sure whether that was going to be an El Nino, but it looks partly an El Nino. And I guess in answering this question, I've also got another question, Isra, probably to you, is that does the department use the Indian Ocean dipole as well as the ENSO for help looking at different weather patterns or across Indonesia? And I think in Northern Australia, we're starting to realise, I think, or the Weather Bureau here, the equivalent of your BMKG, is realising that the Indian Ocean dipole has a very large role to play in our weather. And I would have imagined that the southern parts of Indonesia would also be affected. So I guess that's a question back to Isra.
Mm-hmm. Okay, Pak Isra, there's a question from Pak Graham.
Yes.
The IUD.
Thank you. We use also the ENSO and then IUD also to predict what will be happen in the next 1, 2, or 3 months. Beside the another indicators. But yes, in 2015, there's El Nino years where the fire also occur in the huge massive. And we can see also in the last 2016, 17, it dropped significantly, even the hotspot, both the hotspot and also the burn area also. But we also know that, let's say like this, 2015 in the last fire, that's very huge. And then after that, let's say in 3 years, there will be a lot of fuel in the field, and then it will become susceptible to the fire. So we guess also that this fuel contribute much. Why in 2019 there's a big fire, as well as there's the culture of the local people to do fire in opening their area for their plantations. So both indicators is the community culture and also the full load in the fields become a significant where they ignite the fire. Maybe that's my explanation, Pak Indra.
Okay, thank you, Pak Isar. Then I think we can make some such like a fire prediction, Pak Isar, based on this IUD and ENSO. Okay, thank you. There's another question from Pak Acep. I think this one is for Bob. Of the many gases from fire, is there any gas that is the most dangerous for the health? On the other hand, are there any gases that play a positive role in the atmospheric environment? I think this one is related to the first question from Pak Gusti. Bob?
Yeah, I think there's some gases that are dangerous, probably benzene and formaldehyde. And there's one called HNCO, which we discovered using a new instrument in the laboratory. And HNCO has been linked to cataract formation in people's eyes, whereas most of the other dangers from smoke are cancer, respiratory diseases, or heart issues. There are some beneficial compounds in smoke too, in a way, in the sense that ammonia actually acts like a fertilizer. So, and when you burn a fire, you do put some nutrients into the soil that helps the crops grow better and kills the weeds, kills the pests. So there are some beneficial effects of fire. And as scientists, our job is to, try to produce the data that will allow the public to make an informed decision, how they want to manage the fire. But yeah, there's probably even some of the medicines that are in plants are probably in smoke too. I met a scientist from Malaysia who said his mother used to cure whatever was sick. Whenever he got sick, she would get leaves from the forest and put them on the fire. And then he would stand with a blanket over his head and breathe smoke. And I'm not sure I would prescribe that, but there's, there's definitely all kinds of chemicals. There's thousands of chemicals in smoke. So you can find one that will do everything, I think.
And how about for the second question from Pak Acep? Positive role of the gases?
Yeah, so the positive role would be that, like I said, the ammonia. Like for instance, when fires burn in Indonesia, they may pollution in the cities, including in Singapore, but they'll also send some ammonia, ammonium nitrate in the particles that help make the landscape more fertile in Malaysia. The same thing from Australia. Australian smoke comes to Indonesia. Indonesian smoke goes to Malaysia. We get Canadian smoke in the U.S. So then we give them our smoke from Alaska. So this happens everywhere. And there are a few good things in the smoke, but in general, it's, has a negative impact on visibility and health. And one of the good things is with this fire prediction stuff that you're working on is if you can also predict when the air quality will be bad eventually, then people can take precautions to minimize the bad effects of the smoke, hopefully. Like you can plan to work inside if you can on the day when it's smoky instead of outside, that sort of thing.
Okay, thank you so much, Bob. There's another question here still for you, Bob. This is from Bunita Novita. Bob, it's a really amazing work. So we have a better peat emission factors from more Indonesian samples soon based on your work. Anyway, based on your preliminary data, so in your presentation, why MCE and other parameters from Sumatra is different with the Kalimantan? What are the main differences on peat characteristics from both locations that affect the peat fire emission? It is also interesting to see how IPCC 2014 cite your work 1997 related to combustion factor. GF is 1 is applied for almost all greenhouse gases accounting methods from peat fires in Indonesia. I think the second question is already discussed in the earlier. So Bob, I think this one is related why the parameters from the Sumatra and Kalimantan is different.
Yeah, so I think first of all, that's Pak Bambang and Pak Indra and Mark and the team that collected that data. So that, want to give them credit for that. And they also were at the sites where the smoke was sampled. And so they would probably know more about that. But when peat burns, it burns by smoldering combustion. And smoldering combustion has two parts that happen at the same time. And one is something called gasification, like where you see a cigarette glowing in an ashtray. That glowing combustion is known technically as gasification. And that's one of the sources of gases from smoldering peat. But as the heat from the glowing combustion actually breaks down the peat into smaller molecules that are gaseous, and that's called pyrolysis. So there's two completely different processes that happen, and the characteristics of the peat will control the ratio, the moisture, the density, all those things can affect that. So that's where we'll have to work with the team that was in the field to try to see if we can, figure out what controlled that. There's two levels of analysis. One is how much variability there is, And then can you explain the variability? And we be able to do that because the team in the field not only did a job sampling the smoke, but they did a lot of detailed information on the water table, the weather. They took pictures. So as we get further into the analysis, there's hope that we'll understand the controlling factors better by working together as a team.
Thank you, Pak Bob. Bu Novita, do you have any, Mbak Nisa, do you have any comment on the answer from Bob?
No, thank you so much, Pak Israr. It's very clear.
Okay. And this one is also, thank you, Bu Nisa. This is another question is from Pak Acep Akbar. In my opinion, smoke generated from fires is more horrendous and problematic than the invisible gases in general public. From the fact whether controlled burning can still be done if it doesn't produce thick smoke in the peatland. This one is for Bob. This one is, I think Pak Acep wanted to ask about the difference of the controlled burning and the wildfire. So which one is more problematic to the public?
What?
Because yeah, it's related to the thick smoke in the peatland. It's related to the controlled burning and uncontrolled burning in the peatland. Bob, is the controlled burning in the peatland is still giving some problematic to the health and other issues to the public?
I mean, the biggest thing for any health effect is how much you're exposed to it. So the peat smoke tends to stay close to the ground. That's a problem with the peat smoke. But other things, if you ride a motorcycle to work every day in the traffic and you're stuck in traffic all day, you also get a high exposure. Or if you're in a village where they cook inside the house, right, using biomass fuel for cooking, which we've done measurements of that around the world. That smoke is directly into the house, and so you get a high exposure level. So there's a difference in toxicity between the different kinds of smoke, but the biggest factor in terms of staying healthy is to minimize the exposure to it. So, you know, for instance, when I'm in Indonesia, I was asked if the driver has the AC, ada AC. Can you roll up the windows and run the air conditioning, because minimize your exposure to pollution. So that's the general approach. I don't know if that's helpful or not. Wasn't sure.
I can help, Indra.
Okay, surely, Pak Bambang.
Okay, I'll try to answer what the Pak Acep question. Yeah. Yes, I'm agree with Bob. You know, even our regulation mentioned that the burning only for local people. You know, so it means that the people is not allowed to using fire for land preparations. So then, even for the local people who would like to use the fires on peat, there is also restrictions as mentioned by regulation. For instance, like you cannot use in the dry seasons, and then you should manage it. So it means that the negative impact because of this make the regulation emerge. So even you control the burning, it doesn't mean that the you can have all the access to do that. There is also restriction. Why? Because the impact of it is very dangerous. I think the result of our research already mentioned, and also to answer your questions, because the gas from peat fire that we did in 2015, they also contain gases that very harmful to human, like maybe furandas already, and also the other gases is also very dangerous. I think it's better not to use directly, but again, according to regulations, only for certain people, especially for the local peoples. I think that's all, Indra. Thank you.
Okay, thank you so much, Bambang. Yeah, it's really still a problematic issue for us, Pak Acep. But we hope that one day the peat smoke is never become a problematic again for our life. And I think there's something you wanted to say, Pak Adam. Pak Adam from FAO.
Thank you for the opportunity, but the question is there. Can you hear me? Can you hear me?
Okay.
Okay, so
good,
thanks to all the presenters for their excellent work. I think this project has got a really great team of researchers working on it. They're doing field work, remote sensing, laboratory work. I'd like to ask Pak Isra Alba, what is his most important need for KLK for new data or areas of research that this team, project team, could work on, the NASA project? But also from FAO, we would like to know that so we can help if and where we can with some practical outcomes, or we could try and bring in some other complementary research work. So the question for Pak Isra Alba, thank you.
Okay, please, Pak Isra.
Thank you, Pak Indra, and also Pak Adam for the questions. I think we have a conversation with the FAO since I think early this year, maybe about the February or April, I think. And then we respond also to the FAO, and then we send the letter to FAO, which include the concept note on enhancement of fire danger rating system utilization in Indonesia. And then the second one about the concept note on community-based forest and land fire prevention in Indonesia. But so far, we don't have the response yet from the FAO. I think maybe we need to follow up the discussions about this that we sent a letter, I think in April 2020, I think. So it means about maybe 8 months or 9 months ago that we already sent the letter to FAO and then respond about the request from the FAO. Thank you, Pak Adam.
Okay, thank you, Pak Isra, and for putting me on the spot. It's okay, I understand it's been a problem and I apologize for the delay. We have actually been working on that study on the fire danger rating system, and I'm also pleased to hear you're still interested in the community one, but we didn't have time or money for that. But due to the COVID, we haven't been able to run the workshops or the field or the discussions we wanted, but we will get back to you on that piece of work. Please, there is a letter ready, waiting to be signed by my boss to send you very soon. I'm sorry for the delay. So, if I can come back to my other question for the NASA project, you put me on the spot. I take the strong message, and we will work on it. Thank you. If you could answer for the other one on NASA quickly, thank you. If you don't mind, thank you.
Okay, please, Faisal.
Yes, I think there are several meetings and also attended by Professor Graham Applegate and also Pak Adam. That I'm so sorry that I cannot attend that meeting. It's organized by the FORDA, Forestry Development and Agency in Bogor, because at the same time we have another meeting. You know, in this pandemic COVID, we will have about 3 or 4 meetings in one day, in one single day. So there's a lot of meetings that we have to attend, and sometimes still we have to go to the field. So just maybe months ago I have to go to South Sumatra and so on. Still, do the field work and also the work from office and also work from home. So I think maybe we can later on follow up this our discussion and our concept note maybe next year, I think. Because in these 2 weeks, we'll have a new year. Thank you, Pak Indra.
Okay, thank you, Pak Isar. Adam, hopefully soon we will have a better communication and better cooperation with the KLHK ya Pak Isar ya, KLHK FAO and also this NASA project. Okay, any other question from the participant here? Please, you can ask directly. Okay, if not, I think we can come to the conclusion of this webinar. I take some notes here that the formula of burn pit depth and all of the characteristic of the pit fire is not taking as a general, but it's the site specific, if I'm not wrong. And some components, the different chemical pollutants affected differently to the health. And there is a significant relation between fires and ENSO and also the IUD that is already said. And there is just like different kind of pit fire, pit characteristic may result to the different smoke characteristic from the pit fires. And also the smoke from pit fires, we believe that has a positive ones, but the negative impacts is much more tremendous. And I think the most important of this webinar is, I think we have to write such like a position paper, Pak Bambang, to revise the IPCC. And we can use the link that Pak Gusti Ansari already shared with us. I think that's all for today. Before closing this webinar, there's maybe I think we need some closing remarks from Mark and Pak Bambang. Okay, Mark, you can give some such like a closing remarks first, please.
Okay, I don't know where my video went. Can you hear me? Ah, there we go. Well, I mean, I've just been very impressed with the talks we've had for 3 days now and the level of engagement we've had from people. And I think that we're kind of helping move forward here. And I look forward to seeing this information taken up by Indonesia for application in the IPCC and carbon emissions. And I'm hoping that some of the other information that we will derive here in the coming months and years will similarly assist with those kinds of changes. That's about it. I'm about ready to go to sleep. That's about all I can say. Thank you, everyone.
Okay, thank you, Mark.
And thank you, everybody from IPCC, I want to say, for organizing this. This has been excellent.
Okay, thank you so much, Mark. Have a great night there. So, Bob, Pak Bambang, you want to say something for the closing remarks of this series of webinars?
Okay, first of all, I would like to thank for everybody who involved in these webinars. We have 3 international webinars now that actually, when we discuss about this, is still in big questions because, you know, we are in December and everybody busy, the webinars, but we are lucky that we can run this year's for at least 3 webinars. And also thank you very much for the response, for the audience, and also for the speakers. And I'm sorry to say for our colleagues from US, maybe now is in the middle of the night. And again, thank you very much for your excellent explanation, presentation, Bob, and also Mark as principal investigators, and other colleagues like Graham, Adams, and also Laura, etc. Pak Israr, again, thank you very much. In Indonesia, we can say sekali lagi, saya mengucapkan terima kasih atas perhatian dan juga kepedulian Bapak Ibu sehingga bisa hadir pada acara hari ini yang merupakan 3 seri internasional webinar yang kami adakan. Mudah-mudahan apa yang kami berikan ada manfaatnya. Sekian, terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Pak Bambang, and thank you to Mark, Bob, Pak Graham, Pak Israr, Pak Bambang, and all of the participants here. Thank you so much, and back to our MC, Bu Ati.
Thank you, Pak Indra, for being our moderator today, and to all the great speakers, Pak Bob, Pak Graham, Pak Bambang, and Pak Israel. Thank you for sharing with us. So, ladies and gentlemen, we now come to the end of this event. The third international webinar, Peat, Fire, and Smoke, is the last event of our webinar series in 2020. On behalf of the host and committee, we would like to extend our deepest appreciation to you all for your support in participation. Thank you very much for your kind attention and have a good day. Wassalamualaikum warahmatullahi wabarakatuh.
Oke. Thank you, Bob. Bob.
Terima kasih kepada
Terima
semuanya.
kasih Bapak-Bapak semua.
Terima kasih, Bapak.
Terima kasih.
Thank you.